Okay, welcome everyone for the new lecture. So we'll change gears now, and this time we'll talk about a very important topic, which is computing the independent set in the context of geometry. So several techniques are known for computing independent set for these geometric objects. Some of them we'll look at in the form of exercises, which I'll post later. But one of the most powerful techniques which has been devised is via linear programming. So I'll assume you have some basic background in linear programming. Otherwise, it would be good to go online and get a quick revision of it. We would need very basic facts of linear programming for today's lecture. And I'll just mention those few facts anyways. Okay, so let's get started. So in general, at a high level, the problem that we are looking at is the following, that we have some d-dimensional space, and in this d-dimensional space, we have different objects, right, like this. I don't know, some more. Oops. Yeah, so we are given a collection of these objects, and then we want to pick the largest collection of these objects which are disjoint. So I guess in this case, it will be, I can pick this, I can pick this, I can pick this. So I can pick 3 objects which are disjoint, and I don't think I can add any more. So that will be the largest independent set. Pick the largest subset of disjoint objects. Okay, so that's the problem. So in a different way of looking at it is, we want to pack the space with as many objects as we can, while ensuring that these objects are disjoint. Okay, so that's the problem statement. Okay. So now, as I said, in today's lecture, it will be about solving an independent set problem via linear programming. So let's state some facts about linear programming that we will need. Facts about linear programming. Okay, the first fact that we need is that the objective function and the constraints have to be linear. Right, so they can't be quadratic equations or something. It should be a very nice linear function or a linear equation. Okay. And then the next fact we need is that the number of constraints should be at most polynomial in n, where n is the number of objects that are geometric objects that are given to us as input. And finally, the most important fact that we need for today's lecture is that this LP, if it has polynomial number of constraints, can be solved in polynomial time. That's the goal here. We want to come up with an approximation algorithm, and we want that approximation algorithm to run in polynomial time. And this is one fact of LP that we will need. Then LP can be solved in polynomial time. In terms of n. So these are the only basic facts we need. Yeah, this should be enough to get started. Okay, so what I'll do in today's lecture is actually look at the most simplest geometric setting. And what could be the most simplest setting? It's intervals in 1D, right? So simplest geometric setting, and that is intervals in 1D. Okay, so I leave this as an exercise problem. Let me just draw it out. So you have these bunch of intervals like this. And now it's actually a good exercise for everyone to, it's not very difficult, it's a simple solution. So you can actually solve this, the independent set problem exactly in this case. Solve the independent set problem exactly in just n log n time. Right? So this can be done, not very difficult. So I'll leave this as an exercise. Okay, so what we are going to do today is to actually look at the weighted setting. Today's lecture, we'll look at weighted setting. Okay, so what do we mean by that? By that we mean that there will be some weights associated with these intervals. Maybe this. Maybe if everyone else has. Right, so, and now what's the goal? The goal here is to, again, collect a subset of these intervals which are disjoint, but this time the sum of their weights has to be maximized. Right, so in this case, the answer would be to pick this interval followed by this interval, right? These two. I don't think we can add anything more to this. Okay, so let me just write that down. So what's the goal? Maximize the sum of the weights of the disjoint intervals chosen. Okay, so before we go into this problem, in general, I should tell you that, so here I said the unweighted problem can be solved exactly, but it turns out that if you go to higher dimensions, then say you have disks or say squares, rectangles, then the problem gets hard. I mean, the problems are actually NP hard. And so we are looking for approximation algorithms there, right? The moment you increase the dimension or you start putting weights, right? So turns out for this setting, there is, so for the weighted setting in 1D, turns out there is an exact solution. There's no approximation in that solution. It gives an exact solution. But we'll not look at that today. So the focus today is on actually to come up with an approximation algorithm. And the goal is to teach a technique called randomized rounding with alteration. Right? So write that down. The technique that will be used will be called randomized rounding with alteration. So randomized rounding is well known in approximation algorithms. After writing an LP, you do that. But this alteration is kind of a more recent thing that has come up. So we'll illustrate this technique on this very simple setting of weighted intervals. So that's the goal of this lecture. Okay, so now we can start diving into the algorithmic details. Okay, so we will show an algorithm for approximation. So this is what we'll achieve today. Okay, so let's get started. Let's start by setting up some notation. Right, so let's say I'm given a set I of n intervals like this, and their weights are W1, so on up to Wn. Right? And then so let me just draw a figure as well here. So these are the two endpoints with this interval, two endpoints of this interval. So for the sake of simplicity, let's assume that all the endpoints have a unique x coordinate. In the sense, yeah, no two endpoints are coinciding, and just for simplicity. Okay, so then these endpoints are actually important here while setting up the LP. Okay, so then I'm saying, so I have n such intervals and 2n endpoints, right? So let P1, P2, so on up to P2n be the collection of endpoints of the intervals. Okay, so now time to set up the LP. Again, by LP, I mean the linear programming formulation. Okay, so then the way to do that is we'll define a variable called xi, right, which will either be 0 or 1. So before setting the LP, I should actually be more, I'll go a bit slow for those who are not very comfortable with LP. Let's set up the integer program, right? So we'll associate a variable xi with the interval II, the other I being the small subscript. Okay, and then, so what does this mean? Xi equal to 1 implies I is chosen in the final solution. Else xi is 0. That's the standard way of setting this integer program. Okay, so how does it look like now? So let me write down the integer program. IP. It says, so what's our goal? We want to maximize the weight of all the intervals that we collect, right? So the way to write that is this. So if xi is 0, it doesn't add anything to your solution. If xi is 1, and then it adds its weight wi to the solution. Subject to. So now it's time to write the constraints. Right? This was the objective function. And now here we'll write down the constraints. And what are the constraints here? Constraints here are the following. So I'll write the constraint for each endpoint. Or write down the constraints first, and then we can talk about it later. So the last constraint is easy to see, right? So we are basically saying xi is either 0 or 1 for each interval, right? So you either pick it or you don't pick it. So that's why it's called an integer program, because every variable that we consider here will only take an integer value, which is either 0 or 1. Okay, and now this is the interesting one, the constraint that we have written for each endpoint. Right? So what are we saying? We are essentially saying that, we are given this collection of intervals here. If I pick any endpoint here, so in the final solution, if you look at this point here, Pj, the number of intervals that should intersect this in the final solution should either be 0 or 1, not more than that. Right? That's the definition of the independent set problem. Right? The number of intervals covering this point Pj should be either 0 or 1. And that is exactly being reflected in this constraint that we have written here. We'll look at all the intervals which cover this point Pj and add up their xi's. Right? And that should exactly be less than or equal to 1. Right? So this is how you set up an integer program. Right? Okay, good. But as many of you might know, integer programs are hard to solve. In the sense they're NP hard. You can't expect to solve them in polynomial time. So what do we do? So then we convert this, we do what's called relaxation and convert it into an linear programming problem. And how do we do that? Now we say that the variable that we have, xi, they need not take just these integer values 0 and 1. They can take any fractional value. So that's called a linear program in relaxation. Let me just write that down, and then We'll see how it looks like. Call it the linear program. Everything is the same except the last equation that we'll write. So let me quickly jot this down again. And now comes the final one, which has been changed. So let me use a different color for that. So previously it was an integer program. So we were saying it could only take two values, either 0 and 1. But now we are saying it can take any value between 0 and 1. Now let's say 1/2, or 4, whatever. But it can take any values, right? So one thing to notice is that any feasible solution for the integer program will be a feasible solution for the linear program. Let me write that down. Any feasible solution, by feasible solution I mean a set of values given to xi's which satisfy the constraints. Right? So if I set xi equal to 2, that's not a feasible solution because it doesn't satisfy the constraints. Right? So any feasible solution for the integer program is always okay, in this case I shouldn't say always, in this context let me write it down, is a feasible solution for the linear program as well, right? Because what are the values xi's can take there in the integer program? 0 and 1, right? And those are valid values to keep here as well, right? So pictorially, integer program, this is, so all feasible solutions, right? So a smaller subset is here for the integer program, and all of them will be a valid solutions for LP, right? Okay, good. So now one thing that will be obvious is by this is that the optimal value that you get for the integer program has to be less than or equal to the optimal value that you get after you solve the linear programming problem, just because of the figure that they here and the statement is written above, right? Because you're allowing for more possibilities, right? So maybe there's some assignment, fractional assignment of xi's, which can lead to a bigger value of the objective function, right? So because of that, opt of the integer program is less than or equal to the opt of the linear program. Okay, good. So now that we have set up the linear program, right? So now how can we go about using this linear program now? So let's assume, yeah, we have run it on a linear programming solver and it spits out a value of all the xi's, right? So suppose we solve the LP and this is the value of the xi's that the LP solver gives us. right? Okay. So notice here that if we actually okay, so let's just start with traditional technique. What's the traditional technique? The traditional technique would be to just do randomized rounding, right? So what does that mean? It means sample each interval with probability xi. Okay. So this is very good in terms of the total weight that we will collect in the end, right? So notice that the final objective is to maximize the weight of the intervals that we collect, right? So if we just use this technique, so what would happen? What would happen is that the expected weight of the sampled intervals will be, well, the standard definition of expectation, which is the weight of the object in probability of sampling visit picking II, right? And what's the probability of picking II? It's exactly xi, right? So BWI xi. And what is this quantity here? This quantity here is exactly equal to opt of LP, right? Let's go back here. Let's look at the linear program, right? You see it here, right? Look at the objective function here, right? It's exactly what we are getting here, right? Okay, that's good. But then I hope some of you might have already seen what's the problem with this idea is that trouble is, so let's call this, yeah, the sample, okay. No need for notation here. The trouble basically is that solution need not be feasible. Right? It's highly possible, right? I mean, you're just sampling and it could happen that this guy gets picked and this guy gets picked and maybe this guy gets picked. So then if these three are picked, clearly it's not a feasible solution because they are not disjoint. We have made no attempt in the rounding step. Should probably write it down here that we are doing the rounding steps here. By rounding, what we mean is the LP actually assigns fractional values to these xi's, and now we are trying to round them to either 0 or 1, right? So this randomized rounding that we did here, what it's doing is whoever gets sampled is they are rounded to 1, whoever is not picked, they are rounded to 0. Okay, so now how do we take care of this, right? Well, here is where this technique of randomized rounding with alteration comes in, right? So what's the question we want to address here, right? So the question is, after we pick the sample, can we alter it so that it becomes feasible? Basically, all the overlaps that were happening there, that should not happen. But at the same time, too much weight is not thrown out. Right? In the process of making feasible, you should not throw out so many intervals with large weights that the final solution that remains doesn't have too much weight in it. Right? Then again, it's not useful. So you want to do some alteration so that the solution becomes feasible, but at the same time, the weight remains large. Weight is not lost. Okay, good. So now I'm ready to explain this technique called rounding with alteration. Okay. So let's assume that I1 so on up to In, this is actually an important point here, are sorted in increasing order of the right endpoints. Okay. So this is actually an important point because what we'll actually do is we'll actually do a sweep. So this is the real line. We'll actually start from here and sweep the real line from right to left and access the intervals in that order, from starting from in minus 1, in minus 2, right? So we'll keep doing that. And then, yeah, we'll do something as we reach every interval. Okay, so maybe I should take a new page here because this is an important algorithm now, right? So well, step 0 was the LP, let X be the optimum fractional solution which the LP gave us. Right. So now what's the next step? So we did a randomized rounding there. We'll slightly tweak it. It's essentially the same, but there's an important tweak here. We round each I to 1 independently. Okay, I didn't mention this before, but even in the previous rounding step, we were rounding each, we're picking each interval independently of the other. That's a very important step. Round each I to 1 independently with probability xi over 2, right? And let's denote x prime v the rounded solution. Okay, so now let's set up this set R, which is a collection of all the i's such that they were picked in the sampling process, right? So this is phase 1. So whoever got picked in phase 1 is kept in this set R. And now we'll define another set S, which is initially empty, right? So we want to go from this set R, and we'll delete some elements from R, and whatever is left kind of goes into, sorry, we want to delete elements from R, and whoever is left goes into S, and that will be our final solution. So initially S is empty, and now what do we do? So this is the crucial step. So this fourth step will ensure that the solution will be feasible. Okay, by the way, you should notice here that the sampling rate that we used here was not xi, but xi over 2. That's very important. Right, so slightly lesser chances of an interval getting sampled. Right, that's important. Maybe in the exercise I'll post as to why we needed this. Okay. So now run a for loop for I n down to 1. Do what? Do two things. Actually, not two things. So you check two things actually. If I belongs to R, and okay, something is off here. And S, so we keep adding something to S, right? So we look at the current status of S, and we see if we add this I to it, will this be feasible? Will this set be feasible? S union I is feasible. By feasible, we mean all the intervals in here are disjoint. That's true. Then just do this. You just add, you update S, right? Okay, let's try to do a simple example here. So this is called phase 2, by the way. That was phase 1. And this will be called phase 2. So let's assume that at the end of phase 1, no phase 1, this was a situation, right? So this is the set R. Okay, so now we want to construct S. So as I said, we'll start from the right endpoints. All of them are sorted based on the right endpoints. Right? Let me go back and show you that. As I'm saying, I1 to IN are sorted in increasing order of their right endpoints. Right? So then, okay, so what does this algorithm in step 4 do? First, it will see that, well, this segment, it will see this interval A, and that will get added, right, to set S. So now we're trying to construct this set S here. Because S is empty, and then you look at this interval A was picked in this set R, and it's obviously feasible. Okay, next you go to segment B, and again, B has no conflict with A, so that can be added. Now we visit C, right? Now C has a conflict with B. So C cannot be added to set S, so we discard it, right? Now we go to D. Now D has no conflict with A and B, so that can be safely added. So we add D. And then we visit E. Unfortunately, again, E has a conflict with D, so E cannot be added, right? So what we are left at the end of this is these three intervals A, B, and D, right? So clearly this algorithm ensures that the set it reports finally, the set S that it reports is feasible. Clearly S is feasible, right? So that's not very difficult to see. The real question now is the burning question, right? So what is the expected weight of S? Did we lose a lot in the process of doing this phase 2? Well, but I already gave you the answer that we are getting a 4 approximation. So yeah, so we won't lose too much. And that's the goal now. The goal is to do the analysis and show that this set S actually has a lot of weight in it. Okay, so now let's dive into the analysis. So by the way, I should just write it down that the first phase there was independent rounding happening there. Independent randomized rounding. In the second phase, there is no randomization. It's just there's a greedy. It's greedy in terms of it's a greedy algorithm in some sense, and it is deterministic. Right? So only phase 1 has all the randomization. Okay. So now we'll define some variables here. Two binary random variables for each I. Those will be yi and zi. And how do I define them? I define them as follows. it's 1 if I is in R and Zi is equal to 1 if I is an element of S0 otherwise. So this was basically phase 1. If an interval was in phase 1, I mean it was sampled in phase 1, then yi will be 1. If it survives phase 2 and lands in the set S, then its Zi will also be 1. Okay. So now let's write down some simple observations of these based on these new variables that we have defined. So by linearity of expectation, I'm claiming that the expected weight of this set S will be y equal to 1 to n wi expected value of Zi. It should survive the phase 2 and land in set S, as I said. Right, and this is nothing but wi probability of Ci equal to 1, right? Because it's an independent random variable, you can just write this, right? And this follows simply by linearity of expectation. Okay, what's the next claim I want to make? This is also obvious. Probability of yi equal to 1 is xi over 2, right? Because that's the probability with which each interval is being independently sampled. By independent randomized rounding. Okay, so we'll need this 2 claims later when we do the final step. Now the key thing here is this part here, right? How do we evaluate this, or how do we analyze this, or how do we give a good upper bound on this? Actually a lower bound, right? So how do we give a good lower bound on this, that it will finally, each interval will survive with good probability, right? So if you look at these variables, which ones? I mean, y1, y2, so on up to yn, they are all independent, right? But if you look at z1, z2, so on up to zn, they're not independent. They're highly correlated. Well, yeah, that's obvious, right? Because whether you take a value of, if a zi value takes a value of 1 or 0 will depend on a lot of the other things that are happening before it. But these yi's didn't have that issue because they were being handled independently, right? So because of this, it's not straight away clear how do you compute this value of, compute the probability of zi being equal to 1. Okay, so so let's move on. So next step. So now we want to understand this quantity. We want to understand probability of Zi being 0 given that Yi is equal to 1. Right, so means II is picked in phase 1 but rejected in phase 2. Right, so this is being looked at here. Okay, so again we need some more definitions here. So this is II. These are so the green ones here are so this is the interval II I'm showing you here, and I'm looking at the right end point of this interval II, right? Now, when can it happen that this is not picked, right? So these green segments that I'm showing, sorry, green intervals I'm showing you here are the ones which have been picked in phase 2, right? So remember that we are processing these points very strategically in decreasing order of their right endpoints, right? And all the segments that I've shown here, again, intervals I've shown here, have right endpoints bigger than the black point shown there. I'm saying all these green points, the green intervals, have actually been picked in phase 2, right? So if that happens, then clearly, then II is rejected in phase 2. Okay, so now let me redraw this figure now. Now let me use a different color. So now I'm saying these are segments. Again, I'm using the word segment. I should be saying intervals. Forgive me for that. So now I'm saying these are intervals which were picked in phase 1, right? So then, and we'll give these a special term. We'll call them AI, right? So AI will be a collection of J's such that J is greater than I, right? Because as I said, we are starting from IN minus 1, IN minus 2. So we're looking at all J's which are greater than I, and IJ and II intersect at BI. So I didn't define what BI is, but basically it means for every interval II, the left hand point is AI, the right hand point is BI. Right? So we are basically looking at all these blue intervals which are intersecting this point BI, which are intersecting II, and they're intersecting them at this point BI. And the blue segments can go all the way like this as well. No harm in that. Okay. So now we have defined AI, right? Okay, so now so the claim is if any interval from AI survives in phase 2, then the interval in II is rejected in phase 2, right? This should be obvious by now. So let me not repeat that. Okay. So given this, so we need some more notation here. So in some sense, we want to bound the probability of this bad event happening, right? That somebody from AI gets picked in phase 2. And we want to say that it won't happen with high probability, right? So not high probability, but yeah, we'll show you that. Okay, so now let E be the probability, sorry, E be the, E is always reserved for event, be the event that at least one interval from AI survives in the first phase. Sorry if I'm confusing you here, but just give me a minute. I'll just sort things out here. Probability Ci is equal to 0. Just give me a second. Let me write down it first and then I'll explain. Well, let's see if this equation is true, right? Let's just Try to see if this equation is true. Okay, what am I saying? I'm saying probability Zi is equal to 0. Zi equal to 0 means I did not survive in the second phase, the interval. And what is event E? Event E is saying that somebody from AI okay, I think I made a mistake here. Okay, I should have to go back and correct myself here. I'm sorry about that. So here I said, so again there, no, actually I didn't make a mistake. This AI, the definition of AI is still valid. You're picking all J's which are greater than I, and they intersected BI. Okay, that's the only definition I needed. Okay, so now this statement should be obvious, right? Because we are looking for an upper bound on probability of Zi being 0, it's clearly upper bounded by this event E, right? Okay, good. I hope everyone can see that because, yeah, it shouldn't be that difficult, right? We just need an upper bound on Zi equal to 0, and I'm saying you can safely upper bound it by this thing, probability of E. Right, so now let's try to give a good bound on probability of E. So what's the probability of E? Probability of E is nothing but, write it down. Okay, so what's happening here? So we are saying, this is the usual trick, right? So you want the event that at least one of the interval in AI survived, that is E. So we're trying to ask the question, so that will be nothing but 1 minus the probability that none of the intervals survived. The probability of none of them surviving will just be, because that phase happened, every interval was handled independently. So we can say product of yj's being 0, which means none of them got selected. Right? And what's the probability of none of them getting selected? So each interval was getting selected with probability xj over 2 in phase 1, which means it was not getting selected with probability 1 minus xj over 2. So I just written that down. Okay, so now we claim, so now it's down to some arithmetic now. We kind of done with almost everything. One fine, it's just down to arithmetic now. So the key was just this. We didn't know exactly how to bound Zi equal to 0. So then we said, okay, let's just upper bound it by E, probability of the event E happening. And now we just have to do some arithmetic to get a good bound on it. Okay, so let's go. All right, so now claim. We'll prove this claim, but we'll prove that actually prove this. Right, so let's see how we do that. Okay, so we'll have to work with the many ways of going about it. So one way of doing that is via Markov inequality, which I hope most of you remember, else you can just look it up online. Not a big deal. So it just says, given a random variable, we know its expected value, and how much will it deviate from its expected value. That's one of the first line of thought you get is the Markov inequality. Okay, so what's happening here? So essentially we are saying, okay, given this, okay, I was doing it with red, so let's continue it with red. So you had this interval II, and you're looking at this black point here, right? So the question is, in expectation, how many intervals will stab this black point? By stab, I mean cover this black point. Something's off with my iPad today. Excuse me for that. In expectation, how many intervals of R will intersect this point BI? Well, we look at the constraint, right? If we go to the LP that we had, we'll have to make use of the constraint there. Where is it? Yes. So the constraint that we wrote here, right? I'll just take that. And then, so we wrote that constraint for BI, right? And what did we write there? We said xi plus j times ai is less than or equal to 1, right? So it means, and since we were sampling everyone with probability xi over 2, so the answer for this will be half, right? So you basically have to combine this and this, right? So essentially this constraint is saying that not more than one interval should intersect BI. And we're actually sampling everyone with xi over 2 probability, right? So informally, what we are saying is that at BI, the number of intervals we expect to see is half, right? So let's make it more formal, right? Be the number of intervals from AI selected into R. Okay. So then the expected value of T is J over 2, which is most half, right? So now it's time to apply Markov's inequality, which says probability of, so essentially what we're looking at probability of t being greater than or equal to 1 is upper bounded by probability of t being greater than or equal to 2 times expected value of t, right? Because, yeah, you can check that this direction of inequality is correct. And this is where I'm going to apply Markov's inequality, where I'm trying to see what's the probability of t deviating 2 times from its expected value. And that will be nothing but 1 over 2. That's the standard Markov inequality. Just write it down here. So essentially I just used that here. All right, so what is probability of, so we are saying probability of t being greater than or equal to 1 is just half, right? Which basically means we go back to our previous thing. What that basically means is, hold on. Okay, give me a second. Let me just figure this out. This is just some simple arithmetic, which is confusing me here. Yeah, just give me a second. So then what's left here? We're almost done here. So we have shown that the probability of t being greater than or equal to 1 is less than half. And actually, if you see this, E and T are essentially the same. Right, so yeah, I think I unnecessarily gave more notation, but E and T were essentially the same. So there we go. So E and T are the same. So now I've proven that probability of T, I mean, what I mean is they're not the same, but T greater than or equal to 1 essentially implies E. Okay, so that's, I think that should just state that. T greater than or equal to 1 implies event E, right? Yeah, event E happened. Yeah. Therefore, probability of E is at most half. Okay, good. I'm sorry. Okay, so now simple arithmetic, right? So all the work that we were doing till now was that, this interval I survived the first phase, which is why I is equal to 1, but it could not survive phase 2. So we were trying to get an upper bound for that. We finally did that, but I'm sorry for going very slow and getting a bit confused there, but it's pretty straightforward. So we just plug in that value. Then for this quantity here, where zi equal to 1, condition on yi equal to 1 will become at least half, right? So now we are ready. Prove the final claim. Yeah, just one final step and we're done. So the claim is, we've done all the hard work now. Now it's time to prove that the expected weight of this set S will be at least Wi xi by 4. Okay, and what's the proof? Proof will be, so using some of the previous claims, right? So I proved this here, right? Way in the beginning of the lecture somewhere, this here. This claim here, bilinearity of expectation, will be used here now. And zi equal to 1, the way we'll write it is as follows. Say it's I equal to 1 to n, wi, probability of we'll invoke yi now. Yi equal to 1 times ci equal to 1, condition on yi equal to 1. So this is a standard formula of conditioning, right? So then we've done all the hard work. We have all these values with us. So we just plug them in. This is wi. Probability of yi being equal to 1 is exactly xi over 2. And probability of zi equal to 1, condition on yi equal to 1 is exactly half. So what we end up in the end is wi xi over 4. Done. And now why does this give a 4 approximation? Because let me just do that final step as well. Right, and now this is exactly 1/4 times opt of LP. Right, so you solve the linear programming problem, and these are the xi values that were assigned. So the objective function took this value. And now, as I said in the beginning, the opt of the integer program will be less than this. And this was the real opt, right? So this was the real optimum value. Therefore, it's a 4 approximation. Okay, good. So as you can see, the algorithm was very simple. So instead of sampling everyone with probability xi, we just sampled them with slightly lesser probability, which is xi over 2. And then in the phase 2 was also very simple. We just ensured that as long as the feasibility is maintained, we keep adding the intervals, else we discard it. And it was very important to maintain this order of sweeping them from right to left based on the right endpoints. Right? So that was very important. And the analysis basically relied on the fact that, let's go here. Essentially, this is the crux here. If you're looking at some interval II, and if you look at its right endpoint, then there's a good chance that because of the constraints that we wrote in the LP, a good chance that none of the intervals which have an overlap with BI will be sampled in the set R. And because of that, it will have a good chance of surviving in phase 2 as well. That was the key essence, but I sorry for creating some confusion during the analysis, which does happen to me a lot of times. But if you go through these notes again, things should be very clear. I'll post lecture notes of Chandra as well, from where I took this. Okay, good. So do I have any final comments here? Yes, if time permits, then I will try to teach some advanced material where we look at this randomized rounding with alteration for a two-dimensional problem. The two-dimensional problem of this would be rectangles, right? And again, we want to compute independent set there. So there's a very nice application of course, things get more involved there, but again, alteration will be one of the steps that I was used there. And as I mentioned before, this problem can actually be solved, this weighted version can actually be solved exactly, but that was not the goal here. The goal here was to demonstrate this technique of rounding with alteration. Anything else that I had to say? Yeah, that's pretty much it. Okay, thank you.